And then we're going to look at integrating them together, and then we're going to start cleaning up our OS a little bit. I've already, when I was solving this last night, um, it took me. I mean, I was watching Netflix, but I probably spent 2.5 hours or something on it, and it's working. But it occurred to me that the connecting pieces between the individual things were a little bit blurry, let's call it. So let's talk about the individual pieces, then think about how they connect to each other, and then kind of reset for next week. So let me actually bounce over here. Here, just as a quick starting point. So my thing, when I start up, I just put hello on the screen, and then, so you're seeing me, it's capturing so whatever. So that's effectively handling a single key pressed and, for forever. So that's the starting point. Realistically, we probably want to give them a way of keeping, I'm clearing the frame buffer every single time I catch it. That's why it's not staying up there. But whatever. So it's possible. Let's start with that. So now what I want to do is let's go into the book, and let's go through section by section and talk about the individual pieces and what the roles of those pieces are. And then we can start thinking about why these guys, once we understand the roles and how they relate to each other, then we can look at the code and think about how do we connect these. All right, so let's understand the parts. We talked about this last time, but based on the questions I've been getting, the idea of segmented memory still isn't clear. So let's start with that. What's the purpose of segmented memory? What's the purpose of using a segmented memory address instead of a linear memory address? What problem are we trying to solve? Go ahead.
Memory fragmentation?
No.
No? Okay.
In fact, if you look at how segmented memory actually sort of works, you might even say that you're opening yourself up to the dangers of memory fragmentation by using segments. That, you have to be careful how you do future things in the context of segmented memory. What do you think? Go ahead.
Are we trying to limit a program's available space in memory?
Nope.
Is there a speed thing?
Actually, I would say not a speed thing. In fact, yes, a speed thing in that it might take a little bit more time because we have to translate an address. Because we go from a 48-bit segmented memory address to a linear memory address. Where does this thing actually live in memory, right? The job of segmented memory. So let's think about, because really today segmented memory really isn't necessarily used anymore with 64-bit processors. And that'll make sense here in a few minutes. Not that it can't be used, but it's not necessary anymore. So if we go back to the 386 days, so older processors, what was some things that were really expensive in our computers back then? Memory was really expensive. So if we look at, and one of our understandings here, I'm going to talk about this next. Actually, let me preface it right now, is it occurred to me as I was going through this and based on the questions people were asking that we weren't really paying attention to, or we weren't understanding the problem we were trying to solve. Instead, we were just trying to get something working. Right? Those are different things. We want to consider, so I don't know what's in here. Actually, I want to find out what's in here. Oh, it is a microphone. But I know it doesn't look like it, but this is a 386 processor. Okay, so this guy right here is a 386 processor. What's inside this thing? When I unzip it, I just told you it's a microphone. Okay, what's a 386 processor? It's a collection of things, right? And what's in there? So one of the things that's in there is all these hardware registers, right? We have EAX, EBX, ECX, EDX, which are 32-bit registers, which are made up of 16-bit registers, which are made up of 8-bit registers. So we actually have a whole bunch of effectively hardwired 8-bit registers that are wired into 16-bit, which are wired into 32-bit registers. So we can either deal with single 32-bit values. You know, what's a register? If you had to give me a layman's definition of a hardware register, what would you say?
It's like a small, little tiny chunk of memory that's sitting inside the CPU.
Okay, for what? What's its purpose?
Connect to the hardware.
Hold a value. It's a variable. Hardware registers are hardware-based variables. One of the ways we solve problems is using our memory. We need to remember stuff, and processors no different. If we're solving some problems, we need to be able to put stuff somewhere. And to remember something in hardware, we need a hardware register. All right. Now, hardware registers are expensive, right? Especially back then. Even today, they're still expensive. If we were to price these things out, well, I'm not a CPU builder, but I imagine when they're doing, Intel is working on their next architecture, and they're deciding how many hardware registers to put into this guy and what size, they're going to have to look at a couple of different things, right? They're going to look at, so actually, let's just get these in notes, because this is, I think, important stuff. So, Intel and how many registers? What are things that drive the number of registers you put onto a CPU? Well, one thing's going to be cost, right? Okay, go ahead.
Physical space.
Physical space. Anything else?
Power.
Architecture.
Power, well, this is a chicken or egg thing. This is kind of the architecture. Could be power. Certainly backwards compatibility. Yeah, they can't really yank the AX register because all of the software is related on the AX register. The second you jump to a whole different architecture that no longer has that, all your compiled code that used to rely on AX won't work anymore. Right? Does that make? I mean, that is a legitimately important thing. So, backwards compatibility. So, what if Intel decided that they're going to have, every year when they come out with a new processor, it's going to be an entirely reimagined architecture to make it as much better as possible? Maybe we'd have more capable processors, but the consumer would get pretty ticked off if the software they just bought will no longer run. And the developers would get pretty ticked off if the software they just wrote will no longer run. You can't switch computers because you can't run Microsoft Word on it. Because the version of Microsoft Word that you have just came out yesterday. It was written for last year's architecture.
I feel like keeping GCC up to date would become a lot more important.
Yeah, well, and a lot more impossible. I mean, you have to support like a constantly evolving number of architectures. It already supports a whole bunch of architectures, but it would have to support a whole lot more. All right. But if we're thinking about the cost of a hardware register, I don't know what the actual cost is, but if we're thinking about the 386 processor has several registers. I think I have it up on one of my tabs over here. Oh, okay, so these guys over here. So we have a EAX, which is a 32-bit register. We have AX, which is a 16-bit register. And then we have AL, which is, why is this moving? Yeah, and then we have AL, which is the low side of AX. All right, so we have a 32-bit register made up of 16-bit registers, which is made up of 8-bit registers. And we can get at those things in multiple different ways, but I can store a total across these are general purpose registers, what they're calling their main registers here. So if I want to store, quote, big values, I can store a total of 128 bits of value in these general purpose registers, right? I have 32 plus 32 plus 32 plus 32. That's 128 bits. I can choose how I want to store things in there. So that's something else we're going to talk about today, is treating a register not necessarily just for holding a number. It can also be used for holding multiple pieces of information that we just happen to put. Maybe the first 4 bits or one have a certain meaning. The next 6 bits means something else. The next 16 bits means something else. You know, we just happen to be storing them inside of this 32-bit register, but I'm not looking at the 32-bit register all at once. I'm looking at little parts of it. Like, oh, I stored the number 6 in this nice little 3-bit little section over here. It stores an octal value, just because. But I only need 3 bits for that, so I'm only going to use 3 of my 32 bits. I got 29 bits left over for other stuff. Okay, but now by making that decision, I can no longer treat that entire register as a magnitude value. I can't say, okay, I have 2 to the 32nd power for the 4.2 billion whatever number, because I'm using some of the bits for other things. All right, so idea here would be if we go out and buy memory today for our computer, we buy a 4 gigabyte chip. The price per bit is super cheap, right? Some fraction of a penny would be the price per bit. It would be substantially more expensive than that if we're thinking about the price of hardware registers. The price per bit for hardware registers is way higher.
50 cents.
Potentially, maybe higher. Yeah, I don't know what the number is, but
Right.
you know, the closer you get to the CPU, the more expensive memory is. So if you're Intel and you're coming out with an architecture in the 386 days, but even today, you can't just put an infinite amount of registers in there and just say, hey, memory is really cheap. We'll just put a bunch of them in there because, you know, we don't care about cost. We have an infinite amount of space. You know, backwards compatibility, who cares? We'll just add another 400 registers. If the guys before weren't using it, no problem, as long as we have all the registers they used to use. Another thing we have to think about is heat. You know, the more things you have on there, the hotter it gets, and, you know, blah, blah, blah. So a lot of things play into those decision-making processes for how many and how big the registers are, right? So if we go back in time to the 386 days, 64 bits of hardware register stuff was expensive, right? So, I mean, that was, or 128 bits is what was the 386 for general purpose registers. So they said, we're going to put 4 32-bit registers in there that you can then access subparts of those at the 16 or 8-bit level if you wanted to. But you have 128 bits of storage, any way you cut it. You know, you can't use AL and then use AX, because AH plus AL equals AX. It's the same bits we're talking about. They're just nicknames for the high and low half of those bits. All right, so you have 4 general purpose registers for a total of 128 bits that they give you with the 386. Then they give you some other pointer registers. Now, so that's one side of the equation here. That's what we have in terms of registers. Now, we're still thinking about this as the Intel 386 processor. So all we've talked about right now is what this guy's capabilities are in terms of memory storage. Can a processor do more than memory storage?
Yeah.
A lot more, right? In fact, that's just one of its little tiny things it knows how to do. It needs to be able to remember things, because the way human beings solve problems is we remember things, we ask questions, and we have repetition. Okay, so that assembly language, all those magic tricks this guy knows how to do, the little circuits that are built into this, they have to be able to represent a general purpose problem solving approach that's done in terms of those hardware registers and in terms of asking questions and repetition and being able to jump between labels and things like this. And Intel had to make the initial decision of some of the baseline things that must exist for general purpose computing. Okay, so for example, you saw that there's actually an assembly language instruction for GDT, for that table, right? For the interrupts. Well, that means that's built into the architecture of that chip. This processor, this 386 processor, assumes that interrupts exist, and that the way you're going to manage them is through a GDT table. That's how you're going to manage those things. Okay, this isn't like, oh, if you're the operating system designer, you can choose to do it this way. You have a tool, you got to plug in all the stuff. Your computer's not going to boot up if you don't plug all the stuff into the back of it, right? Or it'll boot up and you can't use the keyboard because you didn't plug the keyboard in. You have to hook all the stuff up in order for this thing to work. And you got to do things the Intel architecture way. Now, as the operating system designer, we can choose some things like we did last time with our memory manager, right? We can decide, this is how I'm going to decide what goes where in my memory addresses. That's a software developer's job, right? We get to decide how we're going to manage our memory. I could use it super efficiently, but maybe in a complicated way, or I can use it inefficiently like we're doing right now, where we're splitting our memory in half and marking bits and using bits, right? So these are all things that are possible for us to do. But those are decisions that the programmer gets to make. Some of these decisions have been taken away from us, though, by Intel, because they're saying, look, if you're going to write an operating system that uses our tool, you have to do things the Intel architecture way. You have access to these memory things. So these are the memory things you have access to. Here's the things, so the idea of segmented memory is assumed, right? Because we have registers specifically for segmented memory. They're built into the architecture. They say we've spent money on hardware registers to support memory, segmented memory. We have this thing called a program counter, EIP, and then shorter is IP. So EIP lets you have programs that are longer, right? Because the program counter says, which line number am I on? So if our program counter starts off as a 16-bit register, that means we can only have 2 to the 16, 65,536 lines of code if our program counter is 16 bits. But
we don't change what the lines actually are.
Well, the program counter indexes where we are in there.
Right.
And it's not lines of high-level code, it's lines of low-level code. 65,536 unique lines of low-level code. Because we can't, if with just IP here, with a 16-bit register, we can't count higher than 65,535. We can't go to line 65,536. We can't count that high. We start over. Now we're back at line 0. Then 1, then 2. You just keep adding 1 to it, 0's back, right? Because we get an overflow and all this stuff. So with a 32-bit, now we can have 4.2 billion lines of code. 2 to the 32nd. So 0 to the 2 to the 32nd minus 1. 2 to the 32nd minus 1 is the highest number we can count in 32-bit math. So that is what, 2 to the 32nd. So 4,294,967,295. That's as high as I can count in 32 bits. If I add 1 to that, I'm back to 0. So now I can only have almost 4.3 billion instructions of low-level code in my computer program. Make sense? Now, that's a lot of lines of code, but it's not an infinite number. At some point, that might be a limitation, right? And we need bigger registers. We maybe the, EIP. I don't even know in modern architecture if EIP is larger than 32 bits. My guess is no, but it could be. You might say, look, you want to have 60. It would be 64 bits would be the next one. And then that's like a 9 quintillion or 18 quintillion number or quadrillion. I don't remember which of those. I think it's quadrillion. 18 point some quadrillion to the 64th.
It doesn't even tell you.
Well, yeah, it's 18.4, and then you got to figure out what those things are, but I think it's quadrillion. A big number. Big number. All right. But again, we are writing an operating system that has to play by the rules of the Intel architecture for all the important stuff, and then the human programmer's rules for everything else, how we want things to work. Make sense? All right, so that's what we're targeting. We have this thing in front of us that already has stuff associated with it. We're not making it up. What we're having Box do for us is we're having Box emulate the i386 architecture. It's saying, hi, I am one of these. I'm a 386 processor, and I'm going to also attach an amount of system memory to me. So I'm going to pretend like I'm a computer. I'm a box that has a 386 processor in it and has these other components that a computer back then maybe would have had, CD-ROM, things like that. And actually, 386 was probably before CD-ROMs, but probably 3 1/4 inch, 3.5 inch floppies were around in 386 days. But, in any case, you get the point. We are targeting that piece of hardware, and we have to write stuff that follows Intel's plan. Okay, that's why if you look in the book, they keep referencing the Intel 386 manual. See that in different places? That's not like just some some book that somebody wrote, for a research paper that talks about, the idea of segmented memory or something. It talks about what your processor that you're targeting can do and how it has to do it. And it's complex, right? We're going to have to, if we get deeper into this OS, we're going to have to keep referencing it. Today, we're going to have to go and reference it. So, the idea here is that that's the problem we're actually solving. We're not just arbitrarily picking ways to do these things.
421.
421 is what?
How many pages are in the programmer's reference manual?
Oh, okay. But we're not just arbitrarily picking this stuff out of the sky and calling them certain things because that's fun. It's a lot of the code is taken out of that manual. You're seeing you're able to find some stuff online and bring in stuff. So some of the code you're going to see. I didn't write all the code you're going to see today, but I wrote the code that makes it do certain things, right? So we're going to see how these different things connect. All right. So this makes sense for registers and the hardware we're targeting, and we have a little bit better picture of why we might have to do some of these things in what seems like a weird, arbitrary way. Go ahead.
I just kind of want to jump back a bit to the question of what is a register. Would it be fair to say that a register is also a portion of memory that the CPU actually knows how to do stuff with? Because like with, your cache and especially RAM, you can only really read and write. You can't really add two numbers while you're sitting there. You'll have to bring them to a register to add them.
No, it depends on the architecture. Some architectures will let you add immediate and store it directly back into RAM.
Oh, okay.
It just depends if it has the magic trick or something.
Right.
But it's the fastest type of memory that's the closest to the processor and is usually also the smallest and most expensive per bit. But I think just think of it as a variable made of hardware. If I need to remember something, I have some choices, and they are in those general purpose hardware registers. The other hardware registers, a lot of them are designed to have a purpose. That doesn't mean that in some conditions you can't sneak a value into one of them. If you look at this architecture over here and you see, here's this F segment. Maybe because I think the code segment and the data segment are often used. Then we have this ES, this extra segment. Maybe that's not used. But man, this F and G segment, they don't even have names. There's a pretty good chance you could hide a value quickly inside the F segment if it was convenient, right? It's like, well, I've already used my other 4 registers for other things, and I have a 16-bit value I need to store just for a moment. Okay, so rather than having to push something onto the stack to clear out a register, you can just kind of sneak it into FS real quick and say, I'll be back in a moment. Just one moment. Yeah, right. So, we can do that because those registers may not necessarily have a value in it at the point in time of whatever you're currently working on. But depending on the architecture you're working with, those registers may or may not be earmarked for a very specific task. So the code segment is going to hold the information of where the code is. Well, if you start storing stuff over that, you're going to break your computer. Not permanently break, but you'll have to restart the computer in order for it to work again because the operating system needed to store the code segment in that place because the architecture demands it, right? And if it's not found there, if that value that's there means something else, like, the number of pages in the manual or something like that, all of a sudden you're going to have, it's no longer pointing to a place in memory. It's going to be problematic. All right, so these are our fences. This is the rules we're playing within. All right, so now we get back to this idea of what is segmented memory. We said that computers our memory used to be really expensive, right? And we only have these things to work with when we are indexing places in memory. So if I throw something into EAX, for example, EAX is a 32-bit register. I can only then address 4.3 billion unique buckets of memory, right? And if we just assume that each bucket of memory is 1 byte big, which in most architectures, actually, we don't treat memory like that. We treat them in larger chunks than that. But let's just assume it's 1 byte big. That would be the most granular way of doing it. If I have that number of bytes, that's the number of, if I have, it's already bytes. If I have that number of bytes, that is times 1024, that's kilobytes, times 1024, that's megabytes. You would only be able to support actually, let's go bigger. I'm sorry, I'm going the wrong direction. So that's kilobytes, megabytes, which is 4 gigabytes, right? So if you had a 32-bit processor where you had a 32-bit register and you could only index 4 gigabytes of unique byte space in memory. So the maximum, if your memory was represented as like a giant array, each bucket being 1 byte big, if you chose to represent memory that way, you can only have 4 gigs of RAM in your computer. That's the most RAM you can have, because you couldn't get 4 gigabytes in one. You couldn't get to the next one because you can't count that high in 32 bits. That makes sense?
So that's where segmentation comes in.
Segmentation lets you address a larger amount of memory than what you could otherwise do in just the 32-bit number. Okay, and how does it do it? Well, we have this idea of segments. So the 386 architecture says that a segment is a 16-bit value, right? So if we're going to look at what that looks like, I want to do this. So a segment is 16 Is it bits or bytes?
You said bits.
I want to say it's 16. Trying to remember if it's 16 bits or 16 bytes. The math will work out the same, just 16 bytes will make you be able to address a more impressive amount of memory. Yeah, so this is 16 kilobytes, so I'm guessing it's 16 bytes then for the segments we're talking about. No, this is 16-bit offsets, so that's fine. So this is 16-bit offsets. And since our segment address is 48 bits, so we have a 48-bit segmented memory address. And this guy is divided. We have 16 bits is the segment by 32 bits is the offset, right? That's what that guy does. So if each segment step is 16 bits, and I can take 65,535 steps, so 65,535 times 16, that means I can step into memory 1 million times. I can get to byte, I guess I can get to byte in memory 1 million, 1+ million, before I have to use my offset. My offset is 32 bits. So my maximum value there is the 4.3 billion, right? So that's this guy, plus 2 to the 32nd. So that means the last byte in memory I can actually address is that guy right there, with segmented memory. So I can address that final bucket in memory, which is a larger value than I could have done before, using just 16-bit offsets. All right, so it lets me map, if I put it into like an Englishy thing here. So this allows us to have larger amounts of memory, and I gave you some math examples here. So a 16-bit register can address 65,536 unique addresses. That's in our linear memory addressing model, or 4.3 billion if we're doing 32-bit. If instead we used it to map, here's that map, that math. If we used it to map a bunch of, I call them starting points. Since we have a starting point and then an offset, we can decide to get our address by going to a starting point here and then bouncing off of that to get to an address down here. This is a logical address somewhere in memory. But now I can address stuff that's farther past what I could have otherwise addressed by just using bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, because now I can go to segment 65,535, offset 4.3 billion off of that. Right? So I can get a lot farther down that road with my counting than I could do if I was just indexing 0, 1, 2, 3, 4 all the way up to bucket 4.3 billion, whatever it was. All right, that's assuming we're using an entire 32-bit register for managing the number of buckets of memory. We might not choose to do that, right? So we're limited on the number of registers we have. So we don't just have registers, coming out the wazoo. We have to be careful about how we use them. So segmented memory is a way of increasing our address space without actually having to have more expensive memory inside of our processors to count that high. All right, so we can then use 2 additional 16-bit registers for our 32-bit address. This calculates the offset of the beginning of each of these starting points, which would then allow us to get up to about 512 megabytes of memory in the 386 days, using our examples of these register sizes. Consider that with Box, didn't we say ours is 32 megabytes? We're pretending like our computer has 32 megabytes of memory. That's what Box has in the configuration file, I think, for ours.
Yeah.
So back then, 512 megabytes of memory would have been a lot of memory. I think if you kind of do the math by today's standards, that's kind of like having 2 terabytes of memory in your computer today, based on kind of what like average memory size. So memory 386 days. If we had 4 megabytes was considered the average for a business machine. So if you went out and bought the stock, fairly high-end computer for a business back then, it would have had 4 megabytes of memory in it. Where today, we might say a stock business class machine would be like 16 gigs of memory. Maybe be less, but let's just say it's 16. So 4 megabytes was considered the average for business. We could support 128 times that. That gives us lots of runway for our operating systems back then with that CPU using segmented memory, right? Our memory can get a lot bigger and a lot more expensive. Back then, and the cost of memory those days, you might have thought this was going to last you forever. Similarly, so in today, if we had 16 gigs of memory in today's, we would be able to support about 2 terabytes of RAM. And for those of you who've worked with like server hardware before, a lot of times the memory limitation on server hardware is 2 terabytes of RAM for that exact reason.
That famous.
Never need more than 32K of memory by Bill Gates.
Exactly.
All right.
He didn't actually say. Yeah.
So does that kind of put some of this in context? Like the purpose of segmented memory is to indirectly access buckets of memory that are beyond how far we could have counted otherwise. It's a trick. It's a math trick. It lets us get farther down that road than we would be able to otherwise because we run out of fingers. All right, makes sense? We get the purpose of segmented memory? All right. All right, so that's the purpose of segmented memory, with the understanding that ultimately we get a linear memory address. We are somewhere down this road, but we can get down this road using 16 bits plus 32 bits to ultimately get us at a starting point plus this offset from that starting point, so we can have a longer road of memory. Okay? And this also introduces this idea of something called a segment descriptor, where a descriptor describes what a segment is for. Now, most of our segments aren't necessarily going to be allotted for something specific, but some of our segments might be, like code segments, things like that. But since we can have 65,536 unique segments, we're probably going to have a lot of segments that are just segments, right? To get deeper into memory. I'm going to go through the last segment so I can get to my last bytes of memory that I can address in this particular system. But ultimately, we end up with a linear address, an index, a bucket in memory that is bigger than we could have counted otherwise. Okay? All right, next thing, global descriptor table. Okay, so this is an array of 8-byte segment descriptors. The first descriptor is always a null, so they give us some examples here. All right, so this guy is a table, somehow. Forget about where it's going to be or any of this stuff. What's its job? All right, so it has to have a first segment in order for all the other ones to work, because as you go through the code here, you see that bucket 0 and bucket 1, if you implement it as an array, bucket 0 and bucket 1 are used to represent this guy. Bucket 2, bucket 3 are for this guy. Bucket 4, bucket 5 are for this guy, so on and so forth. So you kind of needed this first dude to be in here in order for your array to work for all the other ones. So you kind of needed a little front padding that wasn't meant for anything. That's why they just call it the null descriptor. It just makes this data structure work. Okay? But ultimately, what are they doing? They're saying, well, my first descriptor, which is going to be at offset 8 from the beginning, is going to be at, so this is index in the thing. So this is kernel code. This is the kernel data. This is a step of 16. This is not the number 10. What number is this? That's the number 16. 1, 0 in hex this is a 0 in the 1's place and a 1 in the 16's place. All right, so if I'm telling you that it is 16-bit steps for our segments, this is a half step, this is the full step. Right? These are 2 buckets in our array to get to that place. All right, so my kernel code might start here. My next segment starts here. But notice the address range for these guys is the full address space for your memory, whatever memory is. Segments overlap with other segments. They just allow you to jump to, that's kind of where I use that phrase, starting points, different starting points in memory to get farther down the line. Okay? So this is kernel code is read and execute, and data is read and write for what you can do in those areas. So you probably don't want to be able to overwrite parts of your kernel code. That's why this is only read and execute. It's not write. You don't want to overwrite kernel code when your operating system's running. That would be bad. All right. So this is an example of what this guy is. So this descriptor table describes your segments. Make sense? That's what that guy does. Describes the segments. Now notice here that we have, for our GDT, we can represent this guy as a struct, and there's a built-in magic trick in our CPU, part of the architecture of this guy. This guy knows about GDTs. Why does he know about GDTs? Because he's designed to work with segmented memory. That make sense? This Intel product was written to work with segmented memory. Therefore, they included a magic trick in here specifically for loading the GDT table. EAX is the address of where the struct that describes the table lives. So this guy loads into the CPU's architecture the information about that table. That's what that command does. And it's a magic trick that the CPU knows how to do. All right. So far, so good. We're kind of, these things making a little bit more sense at this point. Not so much the how to do it, but the what it is. Okay? These are the privilege settings, so I'm not going to go into those things right now because I want to connect some higher level dots. Then we'll make a second path and look at the details. Okay? All right, so we get what the GDT is for. It describes the segments in my operating system. Make sense? Where at the very least for us, we might say we just have a segment 0 and a segment 1. We have our kernel code and the kernel data. So right now, our kernel code, if we think about our memory manager from last time, is everything before 3 megabytes. And our kernel data is everything after 3 megabytes. That's just because we've arbitrarily treated it that way, but now we have a new way of treating it, right? With this segmented memory and an offset from that, where we might still say we're going to jump 3 megabytes out. We would just do 3 megabytes minus 16 bytes, or 16 bits to be the real starting point of that if we were using segmented memory. Okay, so relatively unimportant how it works. It just lets us address more memory, but we need this GD. In order for segmented memory to work, we need to label our segments, and GDT lets us describe our segments and the rules associated with each of those segments. What you're allowed to do in that area of memory. Can you read it? Can you write it? Can you execute it? That kind of stuff. All right? High level use of that. Next thing, interrupts. What's the purpose of an interrupt? I think I asked this either last class or the class before. I mentioned a really, really, really important, probably the most important thing from your operating systems class with CPUs. What's the purpose of an interrupt? Go ahead.
Context switching?
Yeah, context switching. What is context switching? Why does it exist?
It's where you like back up the registers so that way you don't lose the state of the CPU. Then you interrupt it, do something else, and you can come back to it and kind of pick up where you left off.
Okay. Oh, where am I going here? Well, why would I need to pack up my registers? Go ahead.
You can only have the CPU doing one thing at a time. That
Okay. But can I just leave the registers alone?
Might get overwritten.
Why would it get overwritten? Don't I have plenty of registers? No, I don't have plenty of registers. That's the problem. I have a limited number of registers, and everybody wants to use them, especially the general purpose ones, right? Okay, I don't have an unlimited number of these things. So if one program is currently running on the CPU, and it's getting to use some of the and it's doing its job, and all of a sudden it's interrupted for whatever reason. For us today, it's keyboard, right? But for whatever reason, whoever interrupts it, all of a sudden it's like, look, I was in the middle of using these registers for something. These general purpose registers were for me to remember the stuff going on in my program right now, whatever that is. But now I got to go do something else. I've been interrupted. So I need to store the values of all these because the next guy coming in, presumably, is going to want to use those general purpose registers too. All right? So that context switching is expensive. It's the act of you packing up all your values that you're currently using so that you can reload them later, and then the next guy coming in and putting those values back out there. Now, if we're doing a single programming operating system where you do not allow a second process to come onto the CPU, you wouldn't need to pack them up because you can feel safe that nobody else is going to overwrite them. Like, I'm going to go do my I/O for a minute and stuff, but somebody else might be not using these. But all of a sudden we think about, well, isn't even I/O using registers? Let's go, well, not even probably, right? If we look at this, we wrote this a while ago, our io.s. So right here, if I'm writing stuff out, where's my out? So there's my output to the frame buffer stuff, right? It's like, man, I am messing up stuff in the general purpose registers there. Those are things that the program I just interrupted we're currently using. So he better have saved them. So we can't necessarily worry about another program. We might be having to worry about what is our CPU going to do next in terms of writing to the frame buffer, for example, in this example, right? All right, so we have this idea of context switching. And context switching occurs when the CPU gets interrupted for whatever reason. In modern operating systems, there's a zillion different reasons the CPU might get interrupted. One of them might be it just run out of CPU time. Time to get off the CPU, next guy's turn. In this case, our program gets interrupted because you press the key on the keyboard. That interrupts the CPU. Like, whoa, I gotta go read something from this other guy because there's a device connected to this computer that says that he has something for me. So I need to go someplace else. I'm gonna pack up my bags because I don't know what's about to happen. I've just been interrupted. It could be all sorts of different alarms that just went off, right? But I'm gonna go over here and I'm gonna deal with that. All right, so that's this idea of an interrupt. All right, then we have something called an interrupt handler. The handler is effectively the function that says this is what I do when a certain kind of interrupt occurs. Make sense? All right, so we have a interrupt descriptor table, just like we had a table for our global descriptor table for our segments. The interrupt descriptor table lists the different kinds of interrupts that can exist. Okay, now these guys are described using segmented memory as well. So, because we're using that type of thing to say, here is the type of, this has to do with our handler, right? So when a interrupt occurs, the handler lives somewhere in memory. Where does it live? It lives at this segment, offset by these two values put together. That's my 32 bits of offset. All right, and this is covered by two 32-bit buckets in my descriptor table. Does that make sense? Okay, so bucket 0, for instance, is going to have the high bits of my offset, followed by all these other pieces of information. If the handler is present in memory or not, so whether or not the function that we want to call when we are handling, in our case here, the keyboard interrupt, whether it's already loaded into memory, presumably it would be a 1. And for us, we would just have everything in memory, where this kind of moves into the future thinking of if you have more stuff on your computer, more programs installed in your computer than you have physical RAM. Hard drives are usually bigger than memory, than RAM. Therefore, you might have your whole hard drive filled up with computer programs with code, but only a subset of that code is actually loaded into memory where it gets run from. So 0 or 1 here says, is the code that is going to handle this interrupt, is it currently residing in memory, or is it on the hard drive and I need to bring it into memory beforehand? For us, that world doesn't exist right now because we're not even modeling a hard drive. It's like we have RAM. We have RAM, we have registers, that's what we have, everything's in RAM. Okay, you reset the computer, it's gone. We're not even thinking about long-term storage at this point. All right, but that's what some of these other pieces mean, and this is what I was talking about earlier. This is 32 bits of total space, right? What can I do with 32 bits of total space? I can hold a 32-bit number in there if I wanted to, right? I could put a number between 0 and 4.3 billion, or I can put a number between negative 2.1 and positive 2.1 whatever billion if I want to store positive and negative numbers, signed numbers. But I can also choose not to use that space to hold a single value. I can use part of that space, maybe 16 bits of it, to hold a value that means one thing. Then I can use 1 bit to hold a value that means something else. Then I can use 2 more bits for a value that means something else. I can divide up those bits. They're just little buckets. If you walk into my office, I have that little cube storage thing in there. Each one of these is just part of a bucket in the cube. I can put whatever I want in there. That makes sense? So we're choosing to use this area to store a whole bunch of pieces of information, a 32-bit value to store a bunch of pieces of information about this particular entry in the IDT table. And in fact, we actually need 2 entries in there to fully describe how to handle an interrupt. Right? My interrupt handler lives at this segment selector at this address, offset from that. That's where it is, or where it will be if I have to go and get it. It's where I should load it, but for us, it's always already there. So we're always going to have a handler present in memory as a 1. Okay? Privilege level, what's it running as? Most operating systems just have it as 0 or 1, whether it runs as super user or normal user. Some architectures allow you to have 4 different levels of, but the punchline here is they're giving you, if they're going to allow 4 levels, I need 2 bits to represent the values 0, 1, 2, and 3. That's why they specifically chose 2 bits. Does that make sense? Okay, that wasn't arbitrary. They didn't just say, well, we'll just kind of leave the next 2 bits for this guy. That was to support. So really, if this was for most of our modern operating systems, which is we just use 0 or 1, either it's running as admin or not running as admin, we just need one of these bits, actually. It's always either going to be 0, 1 or 0, 0. That's what it'll be there. All right. What's the... Is that guy just for nothing? Yeah, it looks like he's just a space. He's like a nothing. Size of gate. This is for our logic gates, the size of values that allow you to go into the gates for ands and ors, and other gates, ors, things like that. I don't think the rest of this is anything meaningful to us. And then this reserve thing, who knows? It's probably for some special implementation of it or something like that. All right, so really for us, we only care about the segment selector and the offset. That's actually all we care about. The privileges means a little bit of something to us, but we're just running everything as super user right now. So it doesn't matter. All right, so in this interrupt table, we have a collection of the descriptions of our various interrupts and what to do when they happen. Make sense? That's the purpose of IDT. And the what to do is the handler for it. That is the program, the function, the logic that we wrote somewhere to handle an interrupt when we catch an interrupt. All right, so if we look at this little example, so they're saying let's represent IDT as an array of IDT structs. Okay, we'll look at the struct in a little bit, but effectively the IDT struct, remember that we talked about, it was like the first class, second class, when we talked about packed structures. What that lets you do is it lets you have stuff that looks like this, but you can represent it as a struct with individual pieces, one piece for the offset, one piece for P, one piece for DPL, and then it automatically stores it in the correct subbits for the size of the struct. Right? It's a convenient way for programmers to represent this representation of bits without having to go in and I'm going to set these 2 bits right here to this. I'm going to set these 8 bits to this. It lets us do it in a more convenient way with structs. This goes down into the idea of we like to use C, not assembly, if we can help it, more times than not. All right. So that means in our table is a array of IDT structs. And based on our design up here, we have our 2 different things here. So this first one, the first part is dead. The last part of this one is beef. Let's just focus on those 2 because you can remember those 2, right? That's like the funny joke, dead and beef, because that's a hexadecimal value that sounds funny. Dead is the 16 bits high value for your offset. Beef is the 16 bits low value for your offset. So dead beef is your offset off wherever your 16-bit selector segment is, which in this point, your 16-bit selector segment is right there at 8. So you go to selector 8, scroll up here. What was at 8? Was it a kernel code? So I'm going to go to kernel code, which is index 1 in my GDT. So I'll go to my kernel code area, offset off of that by dead beef. So I go to that point, that segment 1, and then I take a dead beef size hop, whatever that converts to in decimal. Okay, a big decimal number. Dead beef is some big decimal number, right? Okay, so I take a dead beef size hop down memory, and then I'm at a place in memory down there. That's where my handler lives. Does that make sense? How this is working? Or at least more sense? Okay, you see how all these pieces are kind of working together? And I get the feeling as you were working on the homework, that's what was blurry, is how these things connected. Is that safe? We didn't really get, okay, so we see this word GDT, we see this word IDT, we see this word segmented, blah, 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 blah. But what do they have to do with each other? Right, so now I'm hopefully bringing these things together, the connection for those things. All right, so when we look at this specific example here with dead beef, I'm saying go to segment 8, offset dead beef, and then here are the other things that filled out the rest of the rules in here. That's all those bits. The only one we really care about is going to be DPL, so this is only the upper byte 4. So the P, DPL, and then buffer here, because we use 4 bits, which is 1 hextet. Mm-hmm. So 1 hexadecimal digit, a hextet, 0 through 9, A through F. That guy right there is, is a 8. And what is an 8? That's a 0, 1, 0, 0. Mm-hmm. So that is 0, 1, 0, 0. That's what goes into that. So DPL, descriptor privilege levels, is 0, 1, 2, 3. So if this was 1, 0, that is a 2. So that's the level for that one is a 2. That make sense? Okay, so now hopefully this kind of connects the dots back to some of the earlier classes. So all of you have had several classes with me, and I do quite a bit of number conversion stuff. Have you noticed that? Mm-hmm. Moving between bases and stuff like that. So do you see how important that is right here? As human beings, we like to think about decimal. Computers like to represent it in hex, and it's very important that we can think about a hex as a, every hextet can be represented as what, V? This is V's special, it's a nibble. Oh. All right, so a 4-bit value or a nibble represents a single hextet. A hextet is 2 hexadecimal as a digit is 2 decimal, or a bit is 2 binary. You get what I'm saying when I say hextet now? Yeah. So hextets are 0 through 9, A through F. That's the appropriate name for it. If you just want to think about it as a hexadecimal digit, that's fine. Okay, but it's the vocabulary of hexadecimal numbers. All right. So, with that in mind, do we get what these 2 hexadecimal values are now saying? We are packing that information in there where we're saying go to segment address that, offset by dead beef, and play by these rules. And that's where my handler lives for this particular interrupt. Make sense? So when an interrupt happens and we go to the IDT table, we say, I've been interrupted. What do I do? You look up the interrupt that happened. What was the keyboard, 33 or something like that?
32 I was getting.
Whatever. Well, it's in my code. What are the interrupts? Okay, so I got interrupt something or other. Okay, and what do I do? Like, oh, when that happens, I go there. Because that's where my handler code lives. That's where the function that I want to call lives. And what do we want to do in this case here? I want to read something in from the keyboard, and I want to turn it into an ASCII value, and then I want to spit it on the screen. That's how I handle a keyboard interrupt. Make sense? All right, so that's what the IDT table is for. How do I handle interrupts? All right, now this whole CPU state, stack state, these are things that are data structures for helping us do that context switch. When I need to pack my bags up quickly, I need to have some way of storing this stuff so I can get it onto the stack. Because the stack is my place where I can store stuff in memory when I need to get it off the registers. Why do I need to get it out of the registers? Because I don't have a lot of them. And somebody else might need to use them. See, we keep coming back to that pattern. Our old processors and our modern processors, we don't have an infinite number of registers. We're limited to the number of things that we have. So I'm done using it. I gotta pack my bags and put it somewhere. Where do I put it? I put it on the stack. The stack lives in system memory, not a hardware register. It's slower, but it's still a lot faster than a hard drive, which is good because we don't currently have a hard drive in ours. But our stack pointer, SP, points to where that guy lives, and we could push things onto the stack. And what do we push? We maybe push a pointer to the CPU state. We push a pointer to the stack state, so on and so forth, right? So that's how we can store our stuff. All right. Let me skip past the details of that for a second. Loading IDT. Okay, let's skip past that. This is the how, right? Not the what. I want to do the how as a second pass. That gets into the details of it. All right, so do we understand the purpose of the IDT now? What do I do when a certain interrupt comes in? What code do I run? Where is my handler? Where does it live? That's what IDT does. Okay, GDT describes my various segments inside of my computer. We're currently operating with 3 segments: the null segment, which is a meaningless segment, kernel code segment, and kernel data segment. Well, my stuff lives in the kernel code segment. Segment 1, offset 8. Okay? Well, no, segment 1, which lives at byte 8, that's my segment, is 8. And then I offset by dead beef in our example, and that's where this handler for my fictitious interrupt will live for this guy. All right? It will live in the kernel code segment at offset dead beef. That's what it says. So GDT keeps track of my various segments of memory. IDT keeps track of my interrupts and what do I do with them. And it uses the GDT, specifically it uses segmented memory, which we can look up what that segment meant in GDT. But it uses it to tell us where in memory is the code associated with our handler. All right, so now we have this cool built-in thing called a programmable interrupt handler or controller, PIC. So start using hardware interrupts, you must first configure the programmable interrupt controller. The PIC makes it possible to map signals from the hardware to interrupts. The reason for configuring the PICs are, this remaps the interrupts. PIC uses interrupts 0 through 15 for hardware interrupts by default, which might conflict with the CPU interrupts. Therefore, the PIC interrupts must be remapped to another interval. So our CPU has its own set of interrupts that happen in the first 16. And if you're going to use PIC for convenience for handling interrupts, you have to remap those because the CPU's already reserved those first 16. CPU already does its thing for certain things for the CPU to manage. That's something Intel wrote at the factory that you don't get to control, right? You know, you're not allowed to go and control those things. That's Intel's code. So select which interrupts to receive. You probably don't want to receive interrupts from all devices since you don't have code that handles these interrupts anyways. For us, we accept interrupts from one device, right? The keyboard. That's where our interrupt comes from in our current assignment, right? We have one thing that can interrupt our CPU that we're in control of, and that's the keyboard. So we might say that pick one in our pick table is the keyboard. We get to choose that. We get to map that. Okay, and we might just say that's generic input-output hardware. All right, and you can go read stuff on how the PIC data structure works, but at the end of the day, the PIC data structure is a way of mapping an interrupt is a way of knowing when you got an interrupt, what was that interrupt. Instead of just getting random interrupt 1, you know, 1 means keyboard. Does that make sense? It connects those two sides. All right. And then this pick acknowledge, this guy gets called when a particular interrupt comes in, and he acknowledges that I found out that interrupt. When you press the button, the first thing that happens is the pick acknowledges, I've been interrupted. Now it does all the whole context switching, calling the right handlers, looking stuff up on the IDT table, all that stuff occurs as a result of that. Go ahead.
How does it know, like for the various ports, how does it know which memory address?
How does it know which one?
Well, I'm like, I see it says, well, I guess it's more us, but you're choosing memory address X20 or X28. How do we know where those are located? Is it just like a standard thing for like Intel has that, or is that like?
Oh yeah. So I get what you're saying. So where do these guys come from? Yeah. So these are hextats, right? So this is the number 32. So this is 2 times 16, which is 32. 0 times 1. So this is port A is at the pointer to its descriptor is at memory address 32. And then this guy is at 160, right? 10 times 16.
Do we have like a range to look at?
We would. So if you look at, so these guy references, where's the closest one here? But there's an Intel book that talks about, see, they have this reference thing at the very bottom. So this one says that they have this was a good tutorial for PICs, but they also often in here reference the Intel programmers thing.
Yeah, Josh, wasn't it like the
Anybody know which number it was?
He posted it in Slack as well.
Oh, well, it's listed in here somewhere.
There it is, 33.
Oh, yeah, thank you. So this guy is the actual Intel architecture for this particular. So if I click on that and open a new tab, did I put it here? Okay. And then where was the other one that I? Oh, am I not on the internet right now?
I think that's.
Oh, should be.
Because you clicked on the other one, and I think it's still trying to get to it.
Oh, I see. That's why I can't even get. Oh, I get it. I get it. Well, that's unfortunate. Anyways, that document is gonna map some of those things. So let's. So what am I even on right now? Yeah. So there's going to be interrupts. So in that book. For the Intel processor, it'll show you the 16 interrupts from the CPU. And then it'll show you the known interrupts for the how that CPU interacts with common hardware. And then you have open interrupts beyond that that are available if you've done stuff on PCs, there's a thing called IRQ channels, where whenever you install a new device that maybe, Windows didn't know about the day it was written, that device will get installed, the driver will locate an available IRQ, and that'll be the interrupt for that device. So if you have a handheld scanner or something like that, and you press the button on it, that might interrupt the CPU and it says, I'm going to scan something in. Well, that wasn't, the handheld scanner isn't necessarily something that Microsoft put in there as a must-have on every computer, so it might not have its own little slot, so it's just going to use one of the unused interrupts that are in there. But there'll be a list of CPU interrupts in the Intel thing, as well as common interrupts for things that the Intel hardware directly, that's what I was saying is keyboard like 32, 33, whatever it was, but, so that it directly supports. And then there'll be free interrupts that you can add to your own tables to support hardware that you either are building yourself and want to support or whatever. Okay. So, let's stop it right there. Does everything make sense with the lesser, since I haven't shown you the details of the pick thing, but roughly do you get that pick will map a interrupt number to the interrupt type? And for us right now, we only care about one type. In fact, we even assume it's in my code, I don't do any checking. You interrupted me, that's a keyboard. So I could have done mine without pick. Because I don't care what the interrupt was. I'm treating it as a keyboard interrupt. 100% of the time, that's what it is. It's the keyboard. All right. So let's walk through the code for this then. I've reorganized my code some, but I've also thrown a bunch of crap still into io.s. So let's maybe start here with this guy. They use something called macros, even though you could actually get away without doing this, since we are, our keyboard one is a no error code interrupt handler. So some interrupts have an error code that will bounce back, other ones don't. This just more, for instance, let's say you have some kind of thermometer sensor or something like that. It might, when it's too hot or too cold, the thermometer sensor maybe will have an error code that will come off of it. So that interrupt also has the ability to have another value that kind of goes with it. Whereas most interrupts, you press the key on the keyboard, you press the key on the keyboard. We don't need any extra error codes associated with that. I just want to know, how are you interrupting me? If you go, that means one thing. If you go, that means something else. Okay? Except we're representing that as 0 or 1. Okay? Or actually something above 16, 17 and 18, right? For those. All right. But these macro things allow you to handle it. Give me a second. I need to turn my brightness up. I can't see my screen. These macro things allow you to handle these guys generically. So this is something built into NASM. So I think most of you seemed like you saw one of your code examples you found had this macro thing. Actually, they used it in the book, right? The macro thing was from the book. Yeah, all this guy it's saying, I can have a version of my interrupt handler that takes in one parameter. Although I think the book has a syntax error here, right?
Yeah, there's a typo.
Yeah, so this says it takes one parameter. That's what a NASM macro does. So here is a function called no error code interrupt handler that takes one input. Here's one called error code interrupt handler that takes in one input. All right, and whatever that input is here is referenced as %1 down here. All right, so this would be interrupt. So if this was handler 33, this would be interrupt handler 33. And this would be the global code. Remember where, notice I have this extern thing here. We've seen that before in our loader. When we have an extern for main. So that allows us to say, there is a main method that lives somewhere else. Call it. This is a promise that it will be available. There's something that will be available. I can't prove it to you right now, but it will be available. So assuming I've externed something called main, I now allow myself to do that. And now me and the assembler are trusting each other that you know what you're doing. I'm going to assume that you've written that someplace else, and it will be linked and available at runtime. Go ahead.
Is extern like only for these languages, or is it like a?
It's a NASM thing. Yeah.
Because like when we were at the hackathon, there was the programs that we had to deal with all had extern variables.
Mm-hmm.
And so it was just like, what is this? What does it do?
Yeah, I'd have to see it, but it's part of the linker that allows you to say that this will become available external to this. It's defined someplace else, trust me. I just have no way of representing it for you here because it's someplace else. But when you go to execute, it'll be there. Or feel free to die whatever horrible death you choose to die when the kernel crashes. Something like that.
And then what?
Yep.
On the other file, you said the one is not like error code one, it's the number of error code?
Which one here?
Yeah.
Yeah, that's number of parameters, not number of error codes. If this guy is a function, this is how many parameters that function takes. And whatever that parameter is, this guy will become that name of that parameter. Usually it's a number. Okay, so if I'm creating, so for this macro, if I have, and you'll see it here down here in a second, I actually create the handlers. Yeah, see, it is 33. Jack. It's 33.
That's what I said.
I thought I said 33.
You said 32, he said 33 or 32.
I said 33, but like I kept seeing 32 places, but then I tried 32 and it didn't work. It was weird.
Whatever. All right, so down here I'm calling my no error code interrupt handler function, passing it a single parameter, 33. 33 will pass in here. So this will create a global called interrupt handler underscore 33. This will create a interrupt handler underscore 33. And this will push onto the stack a 0 and then push onto the stack 33. What interrupt occurred? That's on my stack now, right? Does that make sense what's happening there? So then what do? I'm going to jump to another place, to my common interrupt handler. We jump to labels. So I'm jumping to common interrupt handler, which is this guy right down here. What does my common interrupt handler do? Context switching. Save all my registers. How am I saving them? Whatever all my registers are, I'm pushing them all onto the stack. Make sense? So I'm throwing everything onto the stack because somebody else might come and start messing up these registers. Then what am I doing? I'm going to call my interrupt handler. Oh, by the way, I have something that's guaranteed to be external called an interrupt handler. What does my interrupt handler end up doing? So this is an io.s. I think I put it in io.h. Kind of cheated then if I should have put it in there as a placeholder just so this is self-documenting, so it's a little bit janky, but if I go into kmain, where did I put my interrupt handler? Oh, did I put it in interrupts? That must be where I put it. Yeah. So notice I have something called interrupt handler underscore 33. That guy will be generated for me by that macro. Now I have a wrapper for it. Right? So that macro specifically created a function called interrupt handler 33 that will handle interrupts for the keyboard because I used that macro to generate that guy for me. So I can create all the interrupts I want to have using that macro code to generate all the different globals for me to wrap. So then inside of interrupts.c is where I have my actual interrupt handler. And this guy will work for all of the interrupts. So this is the extern interrupt handler that exists. So really, I would probably put some if statements in here that say, if it's interrupt 17, do this. If it's interrupt 18, do this. I just assume it's interrupt 33. Safe assumption, because I only created one interrupt. So if I'm even here, it's because it was interrupt 33 as of right now. Okay? And what do I do if it's interrupt 33? Or what do I do if it's any interrupt, as my current code indicates? Well, I'm going to read in the scan code from the keyboard. Okay, that's what the keyboard provides us. It doesn't provide us an ASCII value. It provides us a scan code that we then need to convert. Okay? And I'm going to end up putting that into a character for an ASCII. And we have a function here, keyboard read scan code, which I didn't write. It's just a mapping thing. It's in keyboard.h, I think. So this reads in the scan code, which uses our NB from our keyboard data port. And our keyboard data port is in keyboard.h. So that's where our keyboard reads in from. That would be documented in the Intel thing. The data port for keyboard is 6 times 16, whatever that is. 96. Data port 96. That's what that's where the keyboard reads in on the Intel architecture. All right, so that's what that is. That's a hard-coded number that we can map right up to the Intel documentation. All right, so the data port I'm reading in from is, what did I say, 96?
Yeah, it says 96 when you hover over it also.
Oh, does it? Ha-ha! All right, so if I want to think about this in human or in decimal, I have a whole bunch of ports on the data ports. One of them is port 96. That's where the keyboard flows to. So when I hit a button on here, it's going to flow a scan code to that guy. And what am I going to do with that guy? Go back into keyboard C. I'm going to return whatever this function in B does when I pass it the port to read from. What's in B? That's in io.s. Here's NB down here. We wrote that weeks ago, right?
Yeah.
Okay, what does this guy do? Well, he takes in the address of the IO port, moves it into the DX register. Then he calls a built-in function, right? This in is a magic trick of the CPU. And what it does is it reads from that data port a single byte into AL. But that byte is not an ASCII character. That byte is a scan code. For if you're reading from a keyboard, we have to know the nature of the keyboard. Okay, so if I'm looking down the pipe, what was it, pipe 96? Is that what it was? I'm holding the pipe for pipe 96, and I'm reading from that guy. It's going to pop out a byte-sized thing, an 8-bit value. And I might think that's an ASCII value because that's the way I think about things in the character set, but it's not. It's a keyboard scan code. It's something older, wiser. It's like, this is an old evil. Okay, so it's a scan code. I need to turn that scan code into something else, a more modern ASCII value that I can then do something with. All right, so ultimately, this guy is going to give me a scan code. It's going to return the red byte. So we go back here to keyboard. All right, so this boils down to that scan code and then returns the scan code as a char. So this reads a scan code. Make sense? That's what this guy does. In my handler, what do I do with that scan code? Where's my handler? Oh, here it is. Here's my scan code, which is going to be a char. I read in the scan code, so that guy's something. Then what do? I clear my frame buffer. I have a little frame buffer something or other here that has something called clear frame buffer, and it just goes through and puts spaces everywhere. So clear frame buffer. Blah, blah, blah. All right, that's what it does. All right. Then I get the ASCII value by calling my keyboard scan code to ASCII, passing it the scan code I read in. So that's over here in keyboard. And this is just a big mapping thing for our scan codes. So I'm going to return the ASCII value of bucket scan code. So if I press the T, this is what scan code, this is 16, a Q. That would give me 16. Scan code is 16, which is the letter Q. Make sense? This is a mapping. It's like an old school characters, like old school ASCII. So we have scan codes and ASCII and then Unicode. Just keyboard's been around for a while. Right? So if it wasn't broken, why fix it? Type thing. All right, so we get our scan code and we'll return the character associated with that scan code as a char. What am I doing with that guy? I'm storing it in this variable called ASCII. And then what am I doing? I'm writing it to the very first cell in my frame buffer. And then I'm letting pick know that I have dealt with the interrupt. Pick acknowledge. And do I have a pick thing in here? Pick acknowledge says if the thing you were acknowledging is out of bounds, do this. This is error checking. I didn't write this code. This is just the standard pick code from the tutorial thing. All right. Otherwise, I write out using out B the acknowledgement, which then frees it up. So I wonder if maybe that's what, because didn't you say yours was locking on input?
Yeah, it was. But I think I have this exact same code.
Okay. Because if you weren't acknowledging, well, just because you have the code doesn't mean you're calling it.
Yeah, I was calling pick acknowledge.
Okay.
My interrupt handler.
I'm just trying to think where yours might be diving. But in any case, you have to let pick know that I have acknowledged, I've dealt. You know, here's the interrupt, here's the handler. Handler replies with a thumbs up saying, it's good, I got this. All right. So that's what our handler currently does. If I go back to K-main, what does this guy do? Well, I clear out all my memory. I install the GDT, so that's from segments. Let's see what that says to do. So this initializes the descriptor table. So this, and you read the comments, it talks about the null descriptor being at bucket 0. So this creates the equivalent of what we had, where we had the null descriptor, then we had the kernel code segment, and then we had the kernel data segment. Those are the three segments that are in that table. So we create a pointer to a GDT descriptor. We set the address equal to, these are GDT descriptors up here. So this guy is an array of GDT descriptors. So this is our descriptor count, which ours should be 3, right? We have the null, we have the kernel code, we have the kernel data. So when we build this guy, segment descriptor count should be a 3. There it is right there. That's what was in the table, right? If you looked at the book, it showed you this is what a GDT looks like. We have a very simple GDT that says we got 3 segments. The first one means nothing. The second one means a little something. The third one means a little something else. Outside of that, everything happens in kernel space. All right. These are from the Intel. Actually, all these are from that. So if you remember from the GDT table, I don't know if the network's back up yet, but all the segments overlapped. Let's just go with it. It sounds fun. All the segments overlapped, and they went from 0 to the end of memory. And segment limit, this should be, remember that number? That 1 million number from the very, very, very beginning? So that is memory address 2 to the, so we're offset by 16s, right? So this is segment 2 to the 16th power. Which is 65,535. And then I need to multiply that. Actually, it's subtract. Well, I'll just multiply. You'll see a number. It's pretty close. By 16. So 1,048,576. That's one off. Okay, because I've taken 65,535 16-bit steps into memory to get me to my very last starting point in segmented memory. Make sense? I.e., segment limit. Last starting point in memory. First starting point in memory. We're only using 3 of them. And by 3, I mean 2. Right? We started 8, we started 16. Kernel code, kernel segment, or kernel data. All right, so that explains this, that explains this, that explains this. These are things from the documentation. This would be 2. I'm trying to tell you what that means. Flags are usually something that's set after something happens, so that would be something you would check on, but I used to know what flags actually were for segments. Yeah, maybe pop back in there. All right, so now we're going to actually have our GDT descriptors. How many are we going to have? We're going to have 3 of them. That's how many GDT descriptors we have. Then we're going to initialize the descriptors. So what do I have right here? I have my 2 descriptors, right? So this initializes a descriptor at a particular index. So if I pass it index 0, index 1, index 2, so this initializes a specific descriptor. So it'll go to that index, set the base low and high address. So remember, they're all the same. They overlap each other. They use all of memory. Every one of them did. And then we also have a way of getting to the center of it and then the max address of it. This GDT descriptor, do I define it in segment H? Yep. So this is our packed struct for representing a single entry in the GDT table, which was all of those things that talked about, like the segment address and the different parts that it mapped out for the bits. Install GDT.
What does packed mean?
That is, well, packed is our way. It'll be easiest if I can explain it. Did this guy come back? Oh, this guy did though. So packed is a struct, but packed tells it specifically not to add any padding. Treat it exactly the way this is. And what it allows you to do is it allows you to represent bitmaps like this, where we're saying certain bits mean one thing, another bit means another thing, another bit means another thing. So if we say this whole thing is a struct, we have a 16-bit value in here. We have a 1-bit value that we don't want padded, right? Because that 1-bit value, the smallest we can represent it at is a char, which is a byte. But we only want it to be 1 bit, not 8 bits. So by saying it's packed, we want to not pad it. So as long as we put the right fields into our struct and we say to pack it, it'll be the correct number of bits total, and we're able to then talk about them in terms of something dot this and something dot this and something dot this, as opposed to bits 13 and 14 and bits 15 and bits 16 through 31. It'd be a lot more granular if we had to go in and operate it at the per bit level, or if we could talk to it at a struct level. Like this, I can say I'm going to go to this element of that guy, and it's going to be a 16-bit value. That's 4 plus 4 plus 4 plus 4. 65,530. 0 to 65,536. All right, and our base address means something. This is the base address of that segment, which will be 8 or 16 in the 2 segments that we have when we call these guys. So here's our init segment. Segment 1 has our same segment base, segment limit, because remember, 1 and 2 are both in the first 16 bits, in the first 16-bit segment. We only actually have one segment that we split into 2 halves. We have the first half, which is our kernel code that starts at offset 8, and the second one is the at segment 16, which is where the second segment would actually begin if we had another segment. And that happens because we have 2 pieces to represent our one segment. All right, so we initialize our descriptors. Then we load into GDT a pointer to this GDT. And remember, segments load GDT. I'm pretty sure I put this in io.s. I just threw it somewhere because I said I was watching Netflix, so I didn't want to create new files. So I should have in loader.s something called segments load GDT as a global. Oh, that's not loader.s, I'm sorry, io.s. That's where I threw anything assembly E. Yeah, segments load GDT. And this guy calls that LGDT function, you know, the magic trick on the CPU, loading into it the pointer of the pointer of the guy that I just created over here in segments.c. When I call load GDT, when I pass it a parameter, remember the way parameters are passed, they're pushed onto the stack. So this is the first thing on the stack, and it's 4 off the stack pointer. The stack pointer points to the top of the stack. So this guy right here is the 16-bit pointer value that is represented on the stack at an offset of 4 from the top of the stack. 4 nibbles, 16 bits. Bit 0 through 15 from the top of the stack is the pointer address of our GDT pointer. And that's what this guy is loading. I'm letting the CPU know that that is where you can find my GDT. That's the point where I let my CPU know about the GDT. Make sense? So lots and lots and lots of moving parts, but do we see how it actually is at a more understandable level now when we start understanding how the different pieces work with each other? GDT, the IDT, the PIC is just for managing your interrupts. You don't even need that. I definitely don't need it now. I have no.
Will we need it later on?
You won't. You'll never need it. It'll make life easier as we have more and more interrupts. Let's say yes, you'll need it.
Okay.
But I don't even check PIC in my current thing. I could literally remove it from my code and it'll still work because I just assume every interrupt's the same. I handle it identically. I don't care what it is. All right, so all that stuff adds up. I know we're a few minutes over. Let me just kind of knot this up if you got to go. All that stuff ultimately adds up to, I install the GDT. What's interrupts install IDT? Let's go into my interrupts thing here. It's going to be something very, very, very similar. So here's my interrupts install IDT. And that's for again, I initialize a descriptor for this guy. It sets all the things just like before. Install IDT is going to have my interrupts for my keyboard, which was 33, wherever it was in was it .h? Yeah, 33. So I'm going to say that I am going to initialize a descriptor in my interrupts for the keyboard, and it's going to call interrupt handler 33, which was defined in my macro thing at the assembly level we already looked at. Okay? Then I set the information about that, the IDT struct, and then I call load IDT, passing it I say int here because it needs to be 32 bits. This is the 32-bit address of IDT. Why is it 32 bits? Well, that's 32 bits. That's why I cast it to an int before I passed it, so that if it needed any padding, which we happen to know that it won't, because we wrote the struct in such a way that it will be 32 bits. Unpacked. Or packed, rather. Make sense? All right, so that's why I'm casting it to an int first and then passing it the address of IDT in there. And I'm calling load IDT, which was a global assembly from, again, io.s. I think I put it in here. Man, if I didn't put it in here, where the hell did I put it? Ah, there it is. Here's load IDT. So we'll move into EAX, the pointer to that guy. And then here's my built-in magic trick for load IDT. And I'm loading that memory address. So the CPU knows how to load an IDT. I just had to make sure I gave it the pointer to my pack struct. All right. So that was the end of that. So kmain says set my GDT up, set my IDT up, unmark all my memory, clear my frame buffer. This is just me filling it up with hellos just cuz. And then when I do press the keyboard, it comes into my interrupt handler down here, which reads in my scan code, clears the frame buffer, reads in the ASCII version of that guy, writes it to the cell, and then acknowledges that this guy is now. So there's main without an interrupt. So I have everything there. Now I'll create an interrupt. So there's D. I'm still holding down the key, that's why it's not going away. All right, so I've interrupted it, and it's notified that I've interrupted it. When I let go, that's another interrupt has occurred. This time it read in the scan code for nothing. Well, it's blank. If I press G, interrupt, clear the frame buffer, so on and so forth. All right, make some sense? All right, so for next week, I'm going to upload this code, understand the code, and make it so that you can type sentences. You don't have to read them or anything, just I should be able to type in like AND and it should show up as AND on there and not just, given my code as a starting point, that shouldn't be a huge leap, but I guess I encourage you to try to incorporate my code into your code to get yours into that same working state. All right, so what I'll do is I'll take the assignment that was due today and I'll push it to next week with the additional change on it, because I assume nobody had theirs for today completely working. Is that, I mean, work?
Not like this.
All right, what did it do?
I could read it on startup, but I couldn't update it.
Okay. Okay. Well, I guess whatever. I mean, it won't make any difference to me. And I was saying I can give you points if you did the work for today, but I don't think it'll make any difference in the end, anyways. All right. So questions about any of that stuff? All right. So easy peasy. What? I do know what that is. Yes.